So now we're going to look at one of the applications to understanding concavity, which is finding inflection points. First, we need to understand what is an inflection point. So the definition of an inflection point is let f be a function that is continuous on an open interval and let c be a point in the interval. How many times have we heard that now, right? All right, so if the graph of f has a tangent line at this point c, comma f of c, so that's just a point, then this point is a point of inflection of the graph of f if the concavity of f changes from upward to downward or downward to upward at that point. If we look at the little graph down here, we can see examples of what we're talking about. So this point here, the concavity changed from concave up to concave down. That is what we call a point of inflection. Here, I changed from concave up, from concave down to concave up, point of inflection. Here, I changed from concave up to concave down, point of inflection. So the concavity of f changes at a point of inflection. Note that a graph crosses its tangent line at a point of inflection. So that's a key thing to note, that the graph is going to cross the tangent line of the graph at that point. Now, how do we find those points of inflection? Well, if c, comma f of c is a point of inflection of the graph of f, then either the second derivative of c equals 0, or the second derivative of c does not exist at x equals c. So this is how we're going to find inflection points. We're going to use this information here. So let's just kind of talk about some properties of graphs real quick. I'm going to sum up all of the terms that we've talked about so far. So we have something like this, which we would call a relative maximum right there. Something over here we would call a relative minimum. The inflection point would be somewhere around here. So that's where concavity changed. And then if I actually label concavity, concave down on that interval, and concave up on this interval. So those are the key things we've talked about on a graph. We've also talked about increasing and decreasing as well. So I know that the function is increasing along here. Oops, sorry about that. The function is decreasing along here and along here. And then the function is increasing again over here. So that would be our increasing and decreasing intervals. Okay, so those are the things we want to look for in a graph, and those are the things we're talking about when we're talking about using increasing and decreasing intervals to determine a relative maximum or minimum, or using concavity to determine an inflection point. So let's do an example of finding inflection points. I have this function here. I want to find the second derivative, and then I'm going to use the second derivative to find possible points of inflection, or PPOIs, as I like to call them, because that's a great abbreviation. All right, so I want you to pause the video and find the second derivative. Unpause when you're ready to check, and then we will move on. Pause the video now. Okay, so hopefully you got the first derivative was 6x squared minus 6x. Second derivative then is 12x minus 6. So now we're going to find our possible points of inflection. These are the same. The process here is the same as how we find critical values of the first derivative when we're trying to find relative maximums and minimums, but it's the second derivative. Because remember, that was part of our definition of an inflection point, is that at a point of inflection, the second derivative either equals 0 or does not exist. So I would set the numerator and denominator equal to 0 and solve for x to find possible points of inflection. I'm not calling them critical values because that will get confusing, because we already used critical values from the first derivative. So I'm going to say 0 equals 12x minus 6. And then if I solve, I get x equals 1/2. So this is a possible point of inflection. Okay, now what do we do with that? To find if that is an actual point of inflection, we are going to make a concavity chart. So similar to our increasing and decreasing chart that we used to help us with the first derivative. And again, as I started talking about on the first derivative, on the increasing decreasing chart, I'm going to label this with f double prime so I know that's what I'm dealing with here. This is my 1/2. Let's pick a number. I like to use 0. And then 1 is always nice to work with. So remember, what this tells me is I'm going to plug these into the first derivative. I'm sorry, to the second derivative here. And then I'm going to determine, is it positive or is it negative? So if I plug in 0, I can see that it's negative. If I plug in positive 1, I know that's going to be positive. So what does that tell me? Point of inflection. Nice. Now I need to answer this using derivative speak. So we're going to say, since f double prime of x is less than 0 on negative infinity 1/2, and f double prime of x is greater than 0 on 1/2 to infinity, I know the point 1/2 comma, if I go back up here to the function, if I plug in 1/2, that comes out to be negative 3/2. So I'll write that. So I know f of 1/2 equals negative 3/2. I used a calculator for that. You can do it by hand too. It's not that difficult. So negative 3/2 is, let's see, so since f prime of x is less than 0 on negative infinity 1/2 and f prime of x is greater than 0, point is point of inflection. Or you could say is an inflection point. It doesn't matter. But again, we need the justification. This is our answer here. Let's kind of think about when we did the word problems. You have to answer in the context of the problem. This is how you have to answer the problem. All of this is your work, which is important, and you need to show it. But this concavity chart is not answering where the point of inflection is. Okay, here's a fun little way to remember concavity, because I'm all about fun and concavity. So f double prime is positive. That means we are concave up. And look at that. It's like a smile, right? Look at that. I'll smile. And f double prime is negative. So that's concave down, which is like a frown. Frowns are negative, right? We don't want that. Don't want that. Not gonna have it. Okay, moving on. I want you to try this one on your own. So go through the whole problem. Find the domain, the second derivative, the possible points of inflection, do a concavity chart, and then find any actual points of inflection and make sure to write them using your derivative speak. Pause the video, unpause when you're ready to check. Here we ended up with actually 2 points of inflection. So those are at negative root 3 over 3 comma 3/2 and root 3 over 3 comma 3/2. So I answered my problem in the context of the problem using my derivative speak. Since f double prime of x is greater than 0 on negative infinity to negative root 3 over 3, and f double prime of x is less than 0 on negative root 3 over 3 to root 3 over 3, negative root 3 over 3 comma 3/2 is a point of inflection. Since f double prime of x is less than 0 on negative root 3 over 3 to root 3 over 3, and f double prime of x is greater than 0 on root 3 over 3 comma infinity, the point root 3 over 3 comma 3/2 is a point of inflection. How do we do that? Good question. Okay, so first, recognize domains are all real numbers. because if I set the denominator equal to 0, I'm going to get imaginary results. So then I brought this up as x squared plus 1 to the negative first because we do not want to use the quotient rule when we have a constant in the numerator or in the denominator. Remember? I'm sure none of you did that, right? No one did the quotient rule because we don't want to. That's a waste of time. Time is money. That's what they say. They do. So then I did my chain rule, found my first derivative, negative 4x times the quantity x squared plus 1 to the negative second. I simplified a little bit because now I need to do the second derivative, so here I had to do the product rule. So the derivative first times the second plus the first times the derivative of the second, where I have to do the chain rule again. Now I simplified, got a common denominator. And I wanted to do that because I'm going to have to solve the numerator and denominator. I'm going to have to set them equal to 0, so I need it to be a single rational function. So I got a common denominator, combined like terms, factored, and I end up with my second derivative is 4 times the quantity 3x squared minus 1 over x squared plus 1 cubed. So now I set the numerator equal to 0 and I set the denominator equal to 0. I already knew the denominator wasn't going to give me any, but keep in mind, you still want to think about it. From the numerator, I got plus or minus 1 over root 3. You do not have to rationalize this. We've talked about that before. If you want to, you can. I did in my answer, but I didn't here. So then I made my concavity chart. So f double prime, negative 1 over root 3, 1 over root 3. So then I plugged in negative 1, 0, and positive 1. I saw that when I plugged in negative 1, remember when I say plug this in, I'm plugging it into the second derivative. All I'm looking for is it positive or is it negative? So when I plug in negative 1, it's positive. When I plug in 0, it's negative. When I plug in positive 1, it's positive. Okay? So since I have a change in signs, change in concavity, that means I had an inflection point. So then I answer my problem in the context of the problem, and when I'm saying that, I'm saying I just use derivative speak. Now we understand concavity has to do with the curvature of the graph, and inflection points are where concavity changes. Fun fact, there was a book problem in, I think it was Unit 2 in first semester, where it talked about a point of diminishing returns. That's an inflection point because you're going from, think about, well, it doesn't have to be this, but in that problem, the graph was going from increasing at an increasing rate, which would be concave up, to increasing at a decreasing rate, which would be concave down.